Hello viewers, you're welcome once more. In our class today, we are going to look at under physics, the topic quantities and units. Stay tuned and enjoy the class. So here, we'll briefly describe quantities and units and then go straight into difficult questions under the topic, as we might see in exam. Here we'll describe quantities as the property of a body that can be measured. That thing to which a body is measured is what we refer to as quantity. We used to determine that which we used to determine the magnitude of a measurement of a body is what we refer to as quantity. While unit is the yardstick with which a body is measured. The yardstick with which a body is measured is what we refer to as unit. Now, when you say units are those things we use to differentiate one quantity from another. If you look, for example, if you want to determine time is a quantity measured in seconds. So time is a quantity while the unit of time is second. It could be minutes, it could be hour, and so on and so forth. So you have classes of quantities and units. Quantities and units are classified into two: fundamental and derived. The word fundamental from our basic knowledge of English is basics. It means basics. It means the start that is independent. So from the word, we can say that fundamental quantities are those quantities that are independent of any other quantity. They exist independently. They do not exist by a combination of any quantity. While derived quantities are those quantities that are gotten by the combination of two or more fundamental quantities. I repeat, fundamental quantities are those quantities that are independent of any other quantity. While derived quantities are those quantities that are gotten by the combination of two or more fundamental quantities. Then the same way we define fundamental quantities, we can define fundamental units. Fundamental units are those units that are independent of any other unit. They do not depend on any other unit. They exist on their own. While derived units are those units that are gotten from the combination of two or more fundamental units. So it means that derived fundamental units are the units of fundamental quantities, while derived units are the units of derived quantities. So having known this, let us go further to look at examples of fundamental quantities and units. Examples of fundamental quantities and units. So if we say fundamental quantities and their units. So we look at these basic fundamental quantities. Number one, we have the length. Length is the basic fundamental quantity. We have the mass. Of course, we have three basic fundamental quantities. If you are asked in exam to mention the three basic fundamental quantities, we have the length, we have the mass, and then the time. But we have other fundamental quantities that are not commonly used, which are temperature. We have electric current. We have amount of substance. We also have luminous intensity. That is intensity of light. Luminous intensity. So these are the basic fundamental quantities, and they have their units. Starting with length, the basic unit of length is meter, always written as m, small letter m. The basic unit of mass is kilogram, always written as kg in small letter. The basic unit of time is second or seconds, always written as s, small letter s. The basic unit of temperature is Kelvin, always written as K, capital K. The basic unit of electric current is ampere. always represented with capital A. The basic unit of amount of substance is mole, always represented with MOL. And then the basic unit of luminous intensity is candela, always written as CD, small letter CD. So these are the basic fundamental quantities we have with their respective units. So these quantities, you can see, do not rely on any other quantity for their existence. These other units, you can see as well, do not rely on any other unit for their existence. So if we have known that, but these first three that I have mentioned are the one we call SI unit. If you are asked to mention the standard system international units, they are the length, the mass, the meter, the kilogram, and the seconds. So these are the three basic fundamental quantities and their unit, and they are the ones that naturally have dimensions. There are other ones that at convention, some special conventions, they have dimensions as well. But these are the three basic that we use to form other quantities, which are the derived quantities. So having known that, let us look at derived quantities and their units. Of course, we cannot exhaust the derived quantities and their unit, but let's look at few examples of derived quantities and their unit before we proceed. So some of the basic derived quantities we are going to look at, we'll start with area. Area is a derived quantity. Of course, we know that area is a basic formula for area. Let's say area of a triangle is length times breadth, and length is meters, breadth is meters. So when you combine meters times meters, the unit of area is meters squared. That is meter raised to power 2. Another derived quantity is volume. Volume is a combination. If you say the volume of a cuboid, it is a combination of the length and breadth and height. The volume of a cuboid is length times breadth times height. So when you multiply these three, the length, the breadth, the height, these are just different names given to distance. So the three of them are in meters. So meter times meters will give us meter cube. That is the basic unit of volume. Then we look at another physical derived quantity. Such we have let's say velocity. For instance, velocity is a derived quantity which by definition is displacement over time. Velocity is displacement all over time, and the displacement is a type of distance, but a directional distance, and distance is in meters, time is a second. From our fundamental quantity, we now have meters over second, pronounced read as meters per second, which we can as well write as ms raised to power minus 1. Of course, from the law of indices, we know that m over s is the same as m times s raised to power minus 1. So this is meters per second. That is the unit of velocity. That is also the unit of speed, because speed is a scalar type of velocity, while velocity is a vector type of speed. So speed is distance instead of displacement. Speed is distance over time, and of course we know distance have the same unit as displacement, meter, and of course divided by time. So the unit of speed is still meters per second. These are derived quantities. Why? Because they are a combination of this fundamental quantity. You will see that all these derived quantities that we are seeing here, they are combinations of majorly the first three fundamental quantities that I mentioned: the length, the time, and the mass. So let's go further and look at a few more. If you look at acceleration is a derived quantity which is defined by velocity all over time. It is the change in velocity per unit time. So if you say velocity over time, velocity we have seen is meters all over second, then divided by time over second. That will give us what? Meters per second square, because the meter over second divided by another second will give us meters per second square, which you know I said you can write as ms raised to power, instead of raised to power 2 it will raised to power minus 2, because when you remove the division sign it will now be minus 2. So this is pronounced as meters per second square as the unit of acceleration. So that is how. The one thing about good physics is that physics, if you can remember the formula, you can use it to define. If you can remember the definition, you can use it to get a formula. So if you look at another one, force, we can say that force is the product of mass and acceleration. The mass times acceleration is force. Okay, you can see how we are moving. It is a combination of fundamental quantities. Mass times acceleration. Mass is a fundamental quantity that is represented with the unit of mass is kilogram. Then times acceleration, we have seen, is meters per second squared, and that will give us kilogram meters per second squared, because when you multiply these two things, this is what you are going to get. Remember, this can be written as kilogram meter slash second squared, which is the same thing. So having known this as well, should we mention more? We can go on and on and on and on. Okay, let us look at one more. Let us look at one more. Let us say energy or work. If you say that work is the product of force and distance, okay, we say that work is the product of force and distance, or force and displacement, product of force and displacement, or force and distance in direction of the force. So we can say force and displacement is work. So if we know that force is kilogram meters per second squared times displacement, which is a form of distance in meters as well. If you put these two things together, we are going to have kilogram meter times meters, meter squared per second. Sorry, this is not supposed to have minus because of there is a slash. Kilogram meter squared per second squared. So this is the unit of what? Work. Or you can say kilogram meter squared per second squared. That is 2 raised s raised to power minus 2. That's the unit of work. But we know some of these units, because of the nature of the cumbersomeness of the unit, sometimes we use a single unit to represent this. We represent force using the name of Isaac Newton. So we represent force with what? Newton. Represent force with Newton, written as capital N instead of kilogram meters per second square. So Newton is equivalent to kilogram meters per second. If that is the case, and this one is force times distance, if force is Newton and distance times distance, then it means that work is Newton per meters as well. So this is what we have as derived quantities and units. These are basic derived quantities and units, as you can see, but that is not all. We've not exhausted the list, and I say we can go on and on. It will have no exhaust. We will not be able to exhaust it. So having known these fundamental quantities and derived quantities with their units, we are going to look at another thing that has to do with units and quantities, which we call dimension. Dimension is a way of determining the fundamental nature and relationship of physical quantities. Dimension is used to do a lot of things. To mention but a few, dimension is used for classification of physical quantities. Dimension is used to check unit correction. If a unit is correct, we can use dimensional method to find out. We use dimension to simplify equations. We can also use dimension to identify relationship between quantities. If we look at two quantities, they might have different name, different formula, but when you break it down into their basic dimension, you will realize that these quantities are the same. So it's used to determine the relationship between quantities. Let us stop here. So we'll look at dimension of these fundamental quantities, which will help us to get the dimensions of the derived quantities. The dimension of length is represented usually by the first letter of the word length in capital letter form L, usually put in block brackets. The dimension of mass is represented by capital M. The dimension of time is capital T. The dimension of temperature is theta. The dimension of electric current is capital I. The dimension of amount of substance is capital N, while the dimension of luminous intensity is capital J. So if we know this basic fundamental dimension of fundamental quantities, we can use that to get the dimension of derived quantities. We can use that to get the dimension of derived quantities. But you will realize that most times, most of the questions, especially at the level of WAEC and JAMB, will cover these three. Sometimes they will include current, but most times the derived quantities will always cover these three. So the dimensions that we're going to look at will be limited to these ones. It will not be beyond these ones. So let us look at some WAEC questions that are associated with dimension, so that it will help us see how we can get dimensions of derived quantity. Don't forget you are having this class with myself, Ojobo Hygienist. If this is the first time you're seeing me, remember to subscribe. Click the subscribe button, like, and comment in the comment section. So this is a WAEC question that said, state the dimensions of impulse, acceleration, and work. Now, we are going to solve it. We are not just going to state it because we've not solved. We are going to explain how this is gotten. Of course, the dimension of impulse. Before you are able to determine the dimension of any physical quantity, you have to either know the formula of this quantity or the unit of the quantity. Impulse is represented with I, which is the product of force and time by formula. Product of force and time. So what do we do? To determine the dimension of any physical quantity, we must break down this physical quantity to contain only fundamental quantities. Now, if you look at this, the formula for impulse, we have force and we have time. Time exists in the fundamental quantity, but force is not in the fundamental quantity. So we are going to break down this force until we get those quantities that are in the fundamental quantity, which you mentioned: the mass, the length, the time, the luminous intensity, the current, electric current, the temperature. So these are the things we are expected to use to determine dimension. So having known this, we have known that this is time, it exists in the fundamental quantities, and it has its dimension, which we have written before. So if we break down force, we initially said that force is the product of mass times acceleration. So I can write it mass times acceleration, then times this time that is already here, time. Then if you look again, you see that the mass here is in the fundamental quantity, the time is in the fundamental quantity. It is only acceleration that is not there. So we have to break down this acceleration. We have to know the formula of acceleration. So let's write down again. Mass times acceleration is velocity over time. So we are going to write it velocity divided by time. Then times this time that is existing here. Of course, in our mathematical analysis or mathematical system, if you look at this expression, because it is multiplication, this time can cancel this time and it is reduced to mass times velocity. And then we have mass times what? Velocity. This is how you determine dimension. You begin to break it down until you have only fundamental quantities. Now if you look at mass times velocity, mass is in the fundamental quantity, but velocity is not there. So we have to break down velocity again. We'll write the mass times the velocity. Velocity we know is displacement over time. Velocity is displacement over time. I have stated that before. So, and then some of these quantities will have similar ones, because something like displacement, you might say it is not in the fundamental quantity, but it is there, because length can actually be called displacement, it can be called distance, it can be called height, it can be called breadth, it can be called width, depending on where you are using it. So here it is displacement, this is also length. So it means that this is in the fundamental quantity, mass is in the fundamental quantity, and time also is in the fundamental quantity. So this is complete. The dimension of mass, as we've written before, is capital M, times the dimension of displacement, which is equivalent to length, is capital L, while the dimension of time is capital T. Now this will give us ML over T mathematically, but we do not write dimension in a fraction form. Instead, we make it to be in a linear form, index form. So that is equivalent to ML L, by the law of indices, if this t should come up, it becomes t raised to power minus 1. This is the dimension of impulse. That's the dimension of impulse. That's the dimension of impulse. And I told you usually is put in block bracket, but it is not actually compulsory. It's not actually compulsory, but the way you are solving theory, it is preferable to write it this way: mass times length times time raised to power minus 1. This is the dimension. MLT raised to power minus 1 is the dimension of impulse. Now let's look at the second question that said we should determine the dimension of acceleration. Although from the last question we have seen the dimension of acceleration, but let's assume this is a fresh question in exam that you do not have any question before it. The dimension of acceleration is determined by knowing the formula for acceleration. Acceleration, we said, is what? Velocity over time. We said acceleration is velocity over time. And if you look at velocity over time, time is a fundamental quantity that has dimension, while velocity is not. So we have to break down velocity. You know, this velocity over time can be written as 1 over time times velocity over 1 times velocity, because velocity times 1 will give you velocity over time, and it will return like this. So, but I want to separate this so that I'll be able to break down velocity. I'll be able to break down velocity more. So this is equal to 1 all over time times velocity. The formula for velocity is displacement over time, because velocity is not a fundamental quantity, so we have to break it down again. The formula for velocity is displacement all over time. So with this, we have seen that displacement is a fundamental quantity. Remember, I said it is the same as length, then time. So if we put the dimension, we'll have 1 over capital T times displacement, which is length, is L, all over time, capital T. And we put it together, 1 times L is L, time t times t is t squared. And remember, I said you should not leave dimension in a fraction form. So if you bring this t up, it becomes lt raised to power minus 2 not 2, which is advisable to put in block brackets. So this is dimension of acceleration. Then number 3 asks us to determine the dimension of work. It asks us to determine the dimension of work. What is the formula for work? Work is said to be force times distance. Force times distance is work. Or force times displacement. Let's use displacement because distance is not directional. So we say force times displacement, or if you are using the distance, you have to be a distance in the direction of the force. So it is force times displacement that is work. And we know that displacement is already known as a fundamental quantity, the same as length, while force is not known. So if we break down force again, force is mass times acceleration. I'm solving this as if we've not solved force before, as if this is just the question that comes out in exam. You don't have to call it up from your notes. But if you have solved force before in the previous question, you don't need to resolve again. You just call it up here. But let's assume it's a separate question. Mass times acceleration is force. So write it mass times acceleration. Then times this displacement that is here before. So this is equal to mass is a fundamental quantity, so we've gotten that, but acceleration is not. So we break down acceleration as what? Velocity all over time, as we know, then times displacement, which is here before. Then this time I will move it because time mass is a fundamental quantity, time is a fundamental quantity, displacement is a fundamental quantity. It's only velocity that is not. So I will let velocity to be alone. So if I bring this displacement to this and to this, we have mass, so that I will separate velocity times displacement times velocity, those ones that are numerator, mass times displacement times velocity. Then over time, I can put the time here instead of under velocity because I want to break down this velocity again. So I have not done anything wrong by moving the time either under mass or under displacement or under these two, because that's the only quantity that is at the denominator. So this is equal to mass times displacement all over time, then times velocity is displacement over time. Velocity is displacement over time. From our definition, from the formula, you have this. So if you look at these now, displacement, mass, time, all of them are fundamental quantity. We can now represent them by their dimension. The dimension of mass is m, the dimension of displacement is l, the dimension of time is t, the dimension of this other displacement is capital L, dimension of time is capital T. If you put it together, we have mass times length is mass L squared, T times T is T squared. So dimensionally, it is going to be M L squared. T squared goes up to become T raised to power minus 2. So when a physical quantity goes up, if the power is positive, it will change to negative. If it is negative, it will change to positive. So the dimension of work is ML squared T raised to power minus 2. So this is the dimension of these three physical quantities that we have given as example. This is a WAEC question and we have been able to solve it. Remember, the question said we should just state. They don't need you to solve, but I solved so that you will see how it is gotten. Thanks for watching. See you in our next class. Don't forget to like, share, subscribe and comment.